The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, shall we go? Great. Well, I hope you enjoyed Patriots Day, and now we'll go for the final weeks of the course. And I wanted to start with just a thought about scientific computing and the people who work in it and the problems. So just sort of orientation. And maybe my point is that in part of the subject, the situation is sort of like, just give me the matrix, tell me the equation. I don't want to know the physics behind it, just the form of the equation, and I'll discuss how it could be solved. And to contrast that with what you may often be meeting in your theses, even in projects, where the details, the physical consequences, the actual detailed behavior of the solution is what you're looking for. So somehow there are those two parts of the world, and people who understand the physical problem are on the second side, and people who maybe think just about matrices, like that matrix, for example, that saddle point matrix, are more on the first side, like just give me the matrix and I'll figure out how to solve it, how to solve the linear system. If it's a large linear system, I'll invent preconditioners, study stability, whatever you have to do. But today's lecture is kind of half and half, because that is the framework that we're in. But the problem comes from a real problem in fluids. And it's called the Stokes problem, not Navier-Stokes. So Stokes alone is dealing with this question when there is a diffusion term, and I've normalized the coefficient there, viscosity term, whatever we call it, to be 1. And there is the constraint of incompressibility, constant pressure, divergence P equals 0. Sorry, not constant, but divergence of P equals 0 is a constraint. And how does that, first, let's just make some comment on the physical side of this equation. What we're missing that Navier-Stokes would put in is a convection term, a term of V dot grad V that takes account of the fact that there's a flow here. Things are moving. We're not in a stationary situation. And that term has been dropped. So that's telling us then we are in the case of very, very slow flow, where that term could be neglected. And certainly neglecting that term makes our problem easier. It leaves us with this symmetric matrix. It doesn't make it totally easy, as we'll see, but it's a lot easier than when the convection term, which, by the way, is not symmetric and pushes us outside this framework. If that's present, and of course, in computational fluid dynamics, that's the central problem, you have to deal with it. But so we're taking a model problem that doesn't have the convection, doesn't have that unsymmetric complexity. But actually, it's become more and more important. It's more than a model problem now, because there are a lot of medical applications, say probably the flow that your heart, the flow of your blood pushed by the heart is, you've got to account, that's moving along at a decent rate. But flow into tiny capillaries is slow, and Stokes is a reasonable step. And then actually, Stokes is also going to appear in Navier-Stokes calculations, because often when you have two difficult processes, you do a kind of splitting method, and you solve, you drop one term for half a step. So you take, for example, a Stokes step, and then you do what the fluid forces you to do. You move that process with the flow. Okay, so we're flowing slowly here. Okay. And the nice thing is that this fits our saddle point framework. That's why I'm calling this block matrix S. And you see that it really came from a minimization. The minimization was the problem that leads to the Laplacian. That stands for the Laplace operator with a minus sign to make it positive definite. And then this constraint gets imposed by a Lagrange multiplier, P. So P is the Lagrange multiplier here. Oh, wrong. Divergence V is 0. Incompressible. Sorry. Please. Now that's on the tape. It's now on the tape, right. Divergence V is 0. Okay. Okay. So you remember that this, you remember how our equations looked? Let me just see if I'm going to write the unknowns here, V and P, so that you see what everything is, and that equals F and 0. Okay. So this is now S, so I chop off here. So there you see the equations in the saddle point form. So A is the gradient, and it operates on P. And so P is a scalar. I better say, if I put a little arrow here, V is a vector. It has two components, say if we're in a 2D problem. F has two components. P, the Lagrange multiplier for this constraint. The constraint is just a scalar constraint. The divergence is 0. You remember what divergence means. dv1 dx plus dv2 dy. So those are the two components of V, the vector, and its divergence is 0. And these are, well, with the minus sign, are adjoints of each other. Okay. So what's new that makes this problem worth some study? I guess that up to now, we've taken problems like this, and we've done elimination to get to a single equation. You remember that. So that single equation is A transpose CA. Let's see, what? We're multiplying that row by A transpose C and subtracting. And right, let me do the elimination under here. I multiply the first equation by A transpose C. You see, I'm doing the just give me the matrix mode for now. I multiply by A transpose C and I subtract, so the first equation is still there. C inverse V plus AP is F. But the second equation now, when I multiply by A transpose C, so I just put it up there, and subtract, that produces a 0 there. It produces minus A transpose C AP equals minus A transpose C F. It leads us to this crucial matrix. And in applications up to now, that was the way to go. That was totally satisfactory. We eliminated V, we got an equation for P, we solved it, and then once we knew P, we went back and found V. Okay. So why is this different? Why don't I want to get to A transpose CA, the stiffness matrix if we were in finite elements? Why do I want to stay with this two-field system, which in finite elements is going to be a mixed method of finite elements? I'm going to keep V and P in the problem for a simple reason, that C is in this problem is awkward. C would be the inverse of the Laplacian. C is the inverse of the Laplacian, d second by dx squared plus d second by dy squared. That's what delta stands for. And that's an uncomfortable operator to work with, the inverse here. In matrix language, when we discretize, it won't be sparse, right? The Laplacian is sparse. The Laplacian gives us the 5-point matrix, the matrix with 5 non-zeros on every row, 4 on the diagonal and 4 minus 1s, that matrix that we know, the K2D matrix. But this is its inverse. C is now its inverse. It's the inverse of that matrix K2D that we've studied. And of course, it's full. So taking this step produces a completely full matrix. And all our efficient algorithms for large problems were for sparse matrices. So whereas this one is sparse. I mean, this is the Laplacian. So we have the 5-point matrix sitting here. Here we have a discrete gradient and a discrete divergence. They're all derivatives. And you think of the derivatives as being replaced by differences. All these matrices are sparse. But if we take that fatal step of eliminating to get here, the matrix is full. Because of this fact that the inverse of a sparse matrix tends to be a full matrix. And you don't want to work with it. So we don't want, that's my message, don't want A transpose A when this is not sparse. Okay. So that's the point about this example, which in the notes on the website is the section called the saddle point Stokes problem. Okay. All right. So now we have both a specific example of the Stokes equations, 3 equations really, because this is 2 equations for V1 and V2, and this is the 3rd equation, the constraint. Okay. So we have both that specific example and the general case of how do you, so we're now going to work with that matrix as a whole. We're not going to reduce it to A transpose C, though in principle we could. And the question is one of stability. So like stability is a question that didn't come up for our minimum principles when there were no constraints. And maybe I'll just put a little mention why. So this is the first time we've had to face the question of stability. That meaning what do I mean? That S inverse is under control. I don't mean that it's easy to compute that the inverse of that block matrix. But I have to know that the matrix is invertible. And stability is always like one slight step more than just being invertible. It means it's invertible and you have some control of the inverse. You know, it's not just on the verge of disaster. So stability, we want to know about the inverse of that matrix. That's essentially it. We want to know about the inverse of that matrix. And in the process, we really want to know about the inverse of this matrix. So we may not want to compute it. That was my point. But stability is telling us we have here a matrix that's not positive definite. That's the key issue here. Our saddle point matrix is not positive definite. It has positive eigenvalues and negative eigenvalues. Let me just take some example. Okay, so here's an S. So I have a positive thing there, positive stuff or non-zero stuff there. Say, there's a simplest example I could think of. That matrix is not positive definite. Its determinant is -1, actually. But its eigenvalues are, I mean, they're safely away from 0. It's not singular or close to singular either. Now, the question is, so with that 2 by 2 example, no problem. This equation, well, I could study the invertibility of this particular matrix. I mean, that would be solving differential equations. In other words, I could study the case, are P and V under control if I have a bound on F? Well, they are. But the issue comes when I go to finite elements, when I look at a subspace. Now, so I have to try to make that clear. What I plan to do to solve a continuous problem is to discretize it. So I'm going to, this is my continuous matrix, block matrix, symbolic of the differential equation. And it's okay. Analysis would show that. But the question is, if I approximate V by some finite element, by some combination of finite elements, let me call it VH. If I approximate the pressure by some pressure elements, pH, then I'm sort of projecting the problem down into these finite dimensional, finite element subspaces, and of course F will get projected down to FH, and the matrix, these operators will turn into finite sparse matrices. And the question is that projection safe? So that's really, it's the stability. S inverse is under control. This is okay. But is the projection of S inverse under control? Is the projection of S? So if I project it, is the inverse of that under control? That's the question. And this projection is what comes up in applications. This is a projection of the continuous problem, the differential equation, onto finite element spaces. Finite element trial functions. Okay, so we've spoken a little about finite elements in this course and more in 18085, and you probably have seen them elsewhere. You know that we can approximate velocities by, well, here would be a really important example because it's especially simple finite elements. I take my region, suppose it happened to be that rectangle. I divide that rectangle into small squares. There's a small square. Now, I'm using squares rather than triangles. And in each square, I make some low-degree approximation, low-degree trial function for the velocities and the pressures. And the question is, what functions can I use? And for example, one I would love to be able to use would be, so in each square, I would like to be able to use piecewise constant pressures. Piecewise constant pressure, so pH equal constant in this is in each element. In each element is the square. So pH, a different constant in each element. So that would give me my vector of pHs. There would be one component for every little square. And now what about VH? What trial function would I like to use for the velocities? Constant velocities wouldn't be good. That's, at least, that's further than I'm willing to go. I'll go piecewise linear. Piecewise linear in each square. Now, piecewise linear in each triangle meant that it had the form A plus BX plus CY. Strictly speaking, that's what I should mean by piecewise linear, with a different coefficient A, B, C in each piece. But because we're in squares now, we've got 4 nodal values, and we want a 4th coefficient. This was appropriate on triangles. On a square, we really include the bilinear term dxy. Okay. So we have 4 coefficients, which we can determine from which determine and can be determined from the 4 values of the nodes. Do you see that I'm describing the whole space? Now I cut the region into more squares, and I've described a way of discretizing the differential equation. The weak form of the continuous problem, when I plug in these functions, would give me a matrix problem, a discrete problem that'll have this form. And the question is, how about, do I have any control? So it would give me this projected matrix now, finite dimensional instead of a continuous problem. And the question is, have I still got any control? Well, the answer in for this particular choice of pressure space and velocity space is no. Unfortunately, the matrix that's S that appears instead, the C inverse H, shall I say, it would be like our K2D inverse. That was pretty close to what it would be. And the AH and the A transpose H and the 0, that matrix has a famous null vector for this specific example. I'm asking you to, I'm taking big jumps here, because I just want to say the main point. The main point here is that a null vector appears in this problem. S fails to be invertible, and that null vector is like finite element people know its name. It has a couple of names, actually maybe checkerboard. The null vector is a vector when the pressure is 1, minus 1, 1, minus 1 in a checkerboard pattern over the whole region, and a corresponding velocity. And, well, the trouble is that A times this P, AH times this P is 0. That's what kills you. It turns out that A times that particular pressure is 0. And if you lose control of A that way, you've lost control of A transpose CA, you've lost everything. So So I guess coming back to my opening comments, here's a case in which we have a physical problem, but it falls into a pattern which where the mathematics actually decides, are we able to use the trial spaces that are most convenient? I say convenient rather than most accurate, of course. If I wanted to improve the accuracy, I would go up in the degree. I would take pressures to be piecewise linear and velocities to be piecewise quadratic with more points. And I could check the stability or not, the control of is the matrix invertible or not? And the answer might be better there. In fact, the notes and any book on finite elements has a list of, and I don't plan to make that list here, but it has a list of pressure spaces, pressure elements, and velocity elements, on which the first guy that I've mentioned would be like Q0, degree 0, and velocities Q1, degree 1, and the letter Q being used for quadrilateral. If I divided into triangles, I would use the letter P for polynomial in that case. And this is a fail. This one fails. Well, and then, but other lists would be, how about Q1, Q1? I don't know. I wouldn't bet much on Q1, Q1, and of course I could look at the notes to see what the answer is. Or Q1, Q2, that's probably got a better chance. Or many, many, people are inventing finite elements all the time, and they're having to check the stability or not, the uniform invertibility or not of S. Okay. I just want to say that this one is so attractive because it's so simple that people don't give up on it. They want to go with this. This is a fail, but so stabilized. That one is so attractive, and you know specifically that it's this checkerboard mode that's in the null space. So you just think, how am I going to get that mode out of the null space? And the stabilizing method is you add in, you stick a matrix here for purely numerical reasons, and it'll be a matrix that's exactly, that has this checkerboard pattern so that the checkerboard is not any longer in the null space. Maybe I call it minus some small number times some E matrix. It's often written E. And alpha you keep as small as you dare, but the effect is that it takes this checkerboard pressure out of the null space, and you see the problem was that without that the columns of A were not independent. A times P could be 0, and if those columns are not independent, you're lost. Let me put the 0 back. Why was that a bad thing? I want to now sort of connect it to the matrix theory. If I have this particular pressure and AHP is 0, so that tells me that those columns of AH are dependent. Then the columns of S are dependent, right? If I have something in the null space of AH, then I just put a pressure, this pressure in the null space of AH, then I just take the V to be 0, then these guys don't do anything. And the A times that bad pressure gives 0, so I have a VP, a velocity pressure that's in the null space. Okay. So the way it gets fixed is to stick in some small stabilizing factor there. Okay. All right. Now, that's the specifics of this particular example. Well, I didn't give all the specifics. If I were really on the ball, I would show in detail why that checkerboard appears and kills this choice. I would check each of these other choices, and beside each one I would put fail or success. And when it fails, I would try to identify the failure mode, so that if you wanted, you could stabilize and get rid of that failure mode. Okay. But maybe what I'll do instead is to come to the general question here. So the general question is to deal with this matrix S. Can I write it again? C inverse A transpose 0. I want to look at is it invertible? Can I get some bound on its inverse? What do I have to know? And again, I'll just emphasize here, what's the real problem? Because we saw it right there. The real problem is if the columns of A are dependent. In other words, i.e., in other words, A, P equals 0 has a non-zero solution. Then you're wiped out. Because as I'll just repeat, if the columns of A are dependent, then the columns of S are dependent, the matrix is singular and you're finished. So somehow we have to get some muscle behind A, but remember A is a rectangular matrix. This C is M by M. This A that comes up in the constraint, this is M by N. It has, we hope, more rows than columns. But still, the columns could be dependent, and in this situation they are. Okay. So the question is, we have to get some muscle behind A. And this is the famous condition, so-called Inf-sup condition, that you would find in Professor Bhatta's finite element book. But maybe these notes kind of focus on the heart of the idea. And again, it's in some way it's a condition on A, really, and on the pressure spaces and the velocity spaces that you choose. Okay, so these you could really say are AH, PH, and VH, but I'll skip writing H's on everything now. So I'm down in the discrete case, but I have a sequence of discrete problems that's which are growing as H gets smaller, and the question is, do I have a fixed beta that controls things? And it turns out that this is the requirement, that this Inf-sup condition says that for every pressure, there is a velocity. Every discrete pressure now, there is a discrete velocity such that this holds. So it's sort of forcing A to stay away from 0. This beta is a fixed number, and this sort of is the right normalization that goes with this. You see why it's V transpose AP? Because A, if I look at the quadratic form, V transpose P transpose, the quadratic form with the matrix is always multiply by a vector here, multiply it by its transpose here. Where is the A term? A will multiply P, and it'll be multiplied by V transpose. In the quadratic part, in the energy, is this V transpose AP. And that's what we can't let go to 0, because we're not, if that part fails us, then if we lose these and we have a 0 there, this part on the submatrix can't save us. Right. So before I say anything more about that, let me just emphasize what stability was in the symmetric case. So suppose I had a symmetric, positive definite symmetric matrix. It's got some eigenvalues, lambda 1 to lambda n. Okay. Now, so this is what you see on this board is going to explain why stability is automatic if I'm dealing with positive definite things. So suppose I project. I take this matrix. Let me project in the most direct way. I'll throw away the last row and column. Suppose I throw away the last row and column, so that part is now gone. So these are the eigenvalues of K. And of course, being positive definite, they're bigger than 0. Okay. Now, so that was the whole matrix, but now what I'm going to do is I'm going to project on the first n-1 rows and columns. So I'm going to look at the submatrix K sub n-1. And it has some eigenvalues. Are they the same as those? No way. The eigenvalues of K of this submatrix will be, and you see I'm not in this situation. This was not positive definite. So I'm looking here at the positive definite case. This has some eigenvalues, say mu1 up to mu n-1. These will be the eigenvalues of the submatrix Kn-1. And linear algebra is just like the right place to look for some information on the connection between the mu's and the lambdas. They're certainly not equal. Now here's a question. Here's a first question is, if I take a positive definite matrix with positive eigenvalues, I throw away the last row and column. Do I still have a positive definite? Is that submatrix positive definite? And the answer is yes. The eigenvalues are all positive. And more than that, how about that smallest eigenvalue? Because the smallest eigenvalue is measuring like how close are we to disaster, to singular. Can I say anything about that smallest eigenvalue? And the answer is yes. That the smallest eigenvalue of K n-1 is never below the smallest eigenvalue of the full matrix. So if the full matrix is okay, all the projections, all the subspaces, all the submatrices are even more okay. And up at the other end, at the top end, lambda n, mu n, the top eigenvalue in the submatrix never passes the top eigenvalue in the big matrix. So you see at both ends I have what I want. I have control. If I have some range of eigenvalues for the big matrix, then all its projections are inside that range. And therefore the condition number, which would be the ratio of this to this, is smaller than the condition number of the whole matrix. So the condition number of Kn-1 is less or equal to the condition number of Kn. Okay. So, okay. And that's exactly why working with positive definite matrices is so comfortable. The stability is just automatic. But here we're not working with positive definite matrices. The stability is not automatic, and we need this Inf-sup condition. And I don't know whether to try, maybe I'm a little hesitant to go through the steps that lead from there to there, because this lecture is already asking you to put a lot of things together without details. And the notes do the best job I could do in making those steps simple and clear. And this is what you actually check. You check this condition for any proposed finite element and any different problem. It wouldn't have to be the Stokes problem. Other problems would give us a constraint matrix A, a sort of stiffness submatrix C inverse, and we could check the condition again. Okay, so maybe I'm going to leave that statement for the notes. Okay, so that's this Inf-sup condition that says that, and of course you see right away that if A had dependent columns, which is the big risk, if A had dependent columns, that would mean that AP is 0 for some P, and then there would be no V could possibly be found that would save it, right? If A had dependent columns, that's the bogey, man, that we're avoiding above all. If A had dependent columns, then there would be a solution to AP equals 0. This left side would be 0, the right side wouldn't, and the Inf-sup condition would fail. But the Inf-sup condition tells us, well, what about if there are pressures where AP gets smaller and smaller as the mesh size changes? Then the question is, can I find a V, and so on. So that's the full condition, but not to lose sight of the fact that the central question, the key question, is this deep independence or dependence of the columns of A. Okay, good. So let's see. Maybe that's as much as I want to say about the Stokes example and what it leads to in the finite element world. I guess I'm going to stay for another lecture or two with these minimizations. So maybe I just anticipate slightly the start of the next lecture, because I'm quite pleased about getting this next topic into the series of lectures. And I'll say, let me say what it is. So it's going to be a minimization of an AU minus B squared. Okay. But it's going to be now a case in which, just as this lecture has seen, the possibility comes that the columns of A are not dependent, or not independent, that this problem is in trouble. So I want to regularize this problem. How do I save a problem in which, this is a major application in which A is, say, or columns of A, maybe A transpose A is the easiest thing to say. A transpose A is nearly singular, or just plain singular. I'll say, or singular. How do we rescue the problem? Because numerically and theoretically, it's a disaster as it stands now. Okay. It's ill-posed. So let me introduce that word, ill-posed problem. And let me mention, since I'm just using these last few minutes as a kind of getting the big picture, where do ill-posed problems come from? Where do these things come from? They come from, typically from what are called inverse problems. So often they come from, so the application is to inverse problems. Now what's an inverse problem? An inverse problem is for a differential equation. You know some inputs and outputs, you know some solutions, but you don't know the equation. You don't know the coefficient. So you're trying to determine what are the material properties by looking to see what the outputs are for experimental inputs. And very frequently, you don't have enough inputs to really determine what these, so it's an inverse problem to find the coefficients of the equation given some information on its solutions, some measurements, and of course they're probably noisy measurements. I mean, this is an enormous source of applications, growing in importance. And how do we deal with it? Well, you regularize it. So this is typical of this type of problem. You add on some multiple of something that's safe. Like, for example, u squared. So the result is here that this A transpose A that comes from this problem is, there's an alpha times the identity coming from this problem. I mean, it's an ordinary least squares problem. And it leads us to the matrix A transpose A comes from the first part. But I'm just talking about the standard normal equations. It'll produce an A transpose A from here, but from here it'll produce an alpha times the identity. And of course, just the way this minus E worked up there, here I'm doing it even more directly. I'm pushing the problem away from zero. This alpha, this parameter, and the choice of that parameter is the million-dollar question in this whole subject. But its purpose is to regularize the problem, to take this nearly singular matrix and push it up. You know, see, this matrix, A transpose A, never has negative eigenvalues. The problem is zero or very small positive. So by adding on alpha I push those away from zero. Over there, we had the problem of eigenvalues being positive or negative, and by pushing in one direction, we might just bring a negative eigenvalue right onto zero. That's not our problem in this upcoming lecture. In this upcoming lecture, we know that nothing's negative, but we need to make it properly positive. Okay, so that's what's coming. Can I just say the application that I want to describe is the first one I've given in life sciences. And I hope not the last. I don't know if any of you can suggest, and if you do, if you can, an email would be very much appreciated. Applications of this whole framework in life sciences. So you'll see a particular application of this ill-posed problem in trying to determine gene structure from expressions. Okay, so that's what's coming Friday. And I realize here I'm talking about material that probably is not going to go in your projects because of the timing. I'm thinking that your projects are more likely to build on what you had in project 1 and the material about the basic material about solving large systems and basic minimizations here. Okay, thank you. See you Friday.